Happy Holi to all my friends. And India, this is today Holi is the biggest festival of color. And I wish you all the best and stay safe, be healthy, and let us hope that the world will be free from coronavirus and any other evil forces, and let the color uh, prevails and everybody's life become colorful. So, with this wishes, let us continue our discussion on this auspicious day. I thought that it will be good if we carry forward our um, discussion on execution level control. And in that context, today I'm going to discuss with you a mass spring damper system. Okay, that is perhaps the most important one from control perspective. But prior to that, you know that you have studied a mass spring system, and complete solution we try to give to you so that you will know how the solution behaves. And solution was sinusoidal and also theoretical, because mass spring system tells you that if you perturb, okay, and if there is if it's a free oscillation, then the mass with the spring will oscillate forever. But that will not be the case, because um, if it is in the air, it will experience some damping force, but unfortunately that is not there in the model. Today we are going to discuss a complete model or better model. But even then, that very important observations you have seen, and you have seen that if we just look to the solution, and solution can also be plotted in the Argon diagram or the S plane we call. It is actually a plane of reference where there are two orthogonal axes. One axis is real axis, another axis is called imaginary axis. Okay, imaginary axis with -1. Okay, so the mass spring systems roots will be always complemented in purely imaginary in nature. Okay, so we can also you can check, it's a very interesting one. Only thing you will have to do, that trial solution which we made, a sin theta plus a sin omega t plus b sin cosine omega t. Instead, you can do like this: a to the power st. Okay, so mx double dot plus kx equal to 0. So you just put it here, and you will get two purely imaginary roots. So what does it mean? It means simply that there will be oscillation, and you have seen, okay, the other way also, that x versus t, okay, there will be oscillation, okay, like that, and it will be forever if this is the model, mass spring is the model, because there is no other components in the model which will actually reflect the reality. And there you have seen two phenomena, very interesting phenomena. One is called resonance, okay, and there you have seen the amplitude of oscillation. Amplitude of oscillation actually is increasing asymptotically, and it can create destruction to mechanical structure. All these things we have studied. And also you have seen a beating phenomena where the amplitude of oscillation build ups and die down, builds up, grows and die down like this, okay, within an envelope, okay, sinusoidal envelope marked by this expression. So this is called beating. So beating phenomena is not good, but in some cases the resonance could be desirable in case of many electronic components devices, and in mechanical devices, structural devices, this is bad. Anyway, and bad means what? If bad, then what will happen? So you will have to take care that the forced oscillation, okay, which is being imparted on the system, that frequency should not match with the system's frequency, okay, and in that way you can just get away with many disastrous incidents. So that was our mass spring system. Now we'll talk about mass spring damper system as I have depicted here. You see, this is a mass hanging with uh, hanging with a spring as well as a damper. C is the damping coefficient, K is the stiffness, and my earlier lecture, in the beginning lecture, I have introduced this model, and we are going to just critically examine the model today. Okay, so again, if you draw free body diagram using D'Alembert principle, okay, so these are the forces, spring forces, K time X, and this is damping force. Okay, damping force is actually damping constant time X dot. Okay, and this is inertial force, which is actually, if this is the direction of motion, okay, direction of motion could be also this, then you see simply the fluid diagram will be like this. If this is the direction of motion, then you see the spring will put compressive force, which will be Kx. Damper also, by very nature of these characteristics, always it will actually resist your motion. Okay, so if you are trying to pull, it will push you. You are trying to push, it will pull you. So like that. So it will be like that, and then of course this is the direction of motion. So this is D'Alembert principle. So anyway, these and these will give birth to the same differential equation, which is characterizing the dynamics. Okay. So mx double dot plus cx dot plus kx equal to 0. If we assume that there is no external force, if there is external force, then of course it could be P0 sine omega ft, and we will talk about that. But today it is very interesting for us to know that how, even if perturbation is there, how the system will behave. So let us again, same story, same old story. Let us make a trial solution, because this is a differential equation. There is no straightforward way to solve it. We'll make some trial. Okay. So let us make x equals to a e to the power st is our trial solution. If it is so, then just differentiate it with respect to time. So a s e to the power st. And then again double differentiate it, x double dot equals to a s square e to the power st. Okay, and then you, so if this is the solution, trial solution, okay, so and you have derived x dot, x double dot. So if I put all these values here, it will satisfy the equation, right? So we are doing that only. So m x double dot, this is x double dot. Okay, then c x dot, this is x dot, you see, and then k time x, this is equal to 0. Everybody is with me? Great. Now if you look, a is actually constant, and s is also, and you see e to the power st, just you can just make a little bit simplification. Just we are putting a square plus c by m plus k by m, a e to the power st equal to 0. So when the product of two quantity is 0, then either of them must be 0. But here a is a constant which cannot be 0, non-zero constant. And e to the power st for finite t, actually this cannot be, this is exponential term, right? It cannot be 0. So which one can be 0? A square plus c by m plus k by m equal to 0. So this is called the characteristic equation, incidentally, of this differential equation. You see, this is no more a differential equation. Great, it is an algebraic equation, right? And that's why this transformation we have done. So from differential domain to algebraic domain, we have converted our equation, differential equation. So this is called characteristic equation. Okay. So this is a quadratic equation in S, like in the form of a square plus bs plus small c equal to 0. So if you just compare, a equal to here 1, b coefficient, this is equal to c by m. Sorry, this was S. So b equal to c by m, and small c equal to k by m. So just like you see for this quadratic equation, you have two solutions, minus b plus minus root over of 12 class, right? B square minus 4ac by 2a. eh? So putting these values, I am getting solution for this characteristic equation. So two roots, will be there. So minus c by m plus minus root over of c by m square minus 4, 1 into k by m. Great. So you have just a little bit simplification, minus c by 2m plus minus root over of c by 2m square minus k by m. So the general solution will be, this is different second order differential equation, right? Linear differential equation, otherwise I cannot figure out solution. Okay, I have two roots, each root will give a solution, because you see, if, and there will be two constant because second order system. So this is one root, a1, this is for example corresponding to s1, so s1, so my solution will be, general solution will be x equals to a1 e to the power minus c by m plus c by 2m square minus k by m times t, this t, right? So I have got this solution. This is for h1, okay? And similarly, taking the negative sign, this is for s2. Now here is a concept, okay? So since the system is linear in nature, I can, principle of superposition hold good, and then I can put plus. I can just think of that, okay, I have two roots, each root is giving one solution, and then I will just sum them up to get a general solution, total solution. This is only possible if the system is linear in nature. That is very, very important, right? So why not multiplication, etc., right? Because it's a linear. Principle of superposition holds good for linear system. That is our assumption, okay? And that's why I can get a general solution. So this is a general solution of this differential equation. Just making this trial solution, I have converted the system from differential domain to the algebraic domain, and then I have crank out the solution, okay? So far so good. Now this is the solution provided that c by 2m is not equal to k by m. Why this is important to note? Because you see, if c by 2m is equals to k by m, sorry, this is okay. So if this is the situation, then the quantity under this discrimination becomes 0. Okay, this is equal to this. Then what will happen? Then x will be 1 e to the power, only this term remains here. This is gone. This is only, this one remains here. This is also gone. So a1 plus a2 e to the power minus c by 2m into t. Now a1 is a constant, a2 is a constant. So summation of these two constants is another one constant. So this cannot be a general solution, because now you have only one constant. It's a second order system. There should be two constants, right? So this solution is valid only for when non-zero discrimination, right? That is c by 2m square is not equal to k by m. That is either c by 2m square greater than k by m, or c by 2m square less than m. Okay, so this solution is valid only for this, and for this we will move forward and we will solve it in a different way, so that really it should be having two, it should have two roots. Well, so far so good, right? This is very, very fundamental. We have only used class 12 maths and try to crank out the solution of a system, mass spin damper system. Now here, for mathematical convenience, we would like to express this equation number 10 in the form of uh, a dimensionless parameter called damping parameter zeta. So let us try to understand why it is and how to define it. So let us see when this is equals to this, Cc represents the damping coefficient corresponding to the critical damping condition. What is critical damping condition? When this quantity under the discrimination becomes 0. That means C by 2m square equals to K by m. We call system is critically damped. So in this case, situation, we are thinking that damping coefficient, whatever it is Cc. Damping coefficient corresponding to the critical damping situation. And root over of K by m is equals to omega. Now, C sub C is equals to, from here we are getting 2 root over of mk, okay, because this m, this 2 goes, this m enters here with m square, so m cancels out, so 2 root over of mk equals to, from here also Cc equals to 2m omega. Okay. Now we are defining zeta is a damping factor which is equals to damping coefficient C for other situation other than critical damping condition divided by C corresponding to critical damping condition. So this is dimensionless, right? Because same dimension of C it has, okay? So we can just little bit juggling, C by 2m equals to C by Cc, C sub Cc divided by 2m. Why we are doing this? There is a purpose. So we want to write C by 2m equals to zeta omega, where zeta is a dimensionless parameter called damping factor. Okay. Now using this symbol, that is C by 2m, in place of C by 2m we will write zeta omega. So we are getting from here, see, a1 e to the power, so C by 2m, in place of that we are writing zeta into omega, so zeta into omega plus root over of, so this is C by 2m means zeta square, omega when comes out omega, so omega and this omega we are taking common, so this is omega t. Just take a notebook and do this simple math with me, plus a2 e to the power minus zeta minus root over of zeta square minus 1 into omega t for zeta not equals to 1, because zeta equal to 1 corresponds to critical damping situation. For that, this is not the valid solution. We will solve it afterwards. Okay, now let us consider two cases. Now you see, very interesting one thing you should remember, C, M, K, what they are? They are system parameter. M is mass, K is spring stiffness, C is damping constant. And you see, the beauty is this e to the power, this quantity is always negative, irrespective of what M, C, K values are. That some students have difficulties in understanding. So you see, whatever may be, there is this greater than mk, this less than mk, so this is going to be negative. Why? Because e to the power minus c by 2m, and in one place you have under discrimination c by 2m square, that is equivalent to this, and you are subtracting some quantity, and when it will come out, it will be a positive quantity, but it will be less than c by 2m. So as a result of that, negative this quantity plus some quantity which is less than this negative quantity. So negative sign will prevail. So this will be irrespective of whatever, has to be positive quantity, of course. And you see, these are system parameters, right? M, K, C, these are the system parameters. So they has to be positive. So if they are positive, irrespective of this is less than or greater than or whatever, right? You have seen this is negative definite. So e to the power something negative, okay? look here. So minus some quantity minus some quantity, okay, which is some less than that. So minus this, more negative. Huh? So irrespective of whatever values C, M, K are, e to the power minus something plus here also e to the power minus something. That's a great thing of second order mass spring damping system. As long as these are positive quantity, this is the case, okay, and it has great consequences. We'll discuss about that. That's why the control people love to model system as a second order system, okay, because roots are always negative, okay. They can be equal maximum, that is, okay, I will tell you this story actually. In the Argon diagram or S plane, so this is real axis and this is imaginary axis, okay. So where the roots will be? Can the roots ever, for any value of m, c and k, ever on the right hand side? No. The roots could be here, or roots could be overlapping, or roots for underdamped, one roots could be here, another roots could be here. The reason I told you, right? Always negative. So this is the real axis, okay. In case of underdamped situation, there will be imaginary component. We will discuss all these issues. But this is great observation. This observation is from here. So whatever values m, say k may have, the e to the power something will be always negative. And if we plot them in the S plane or Argon diagram, then the roots will be always negative half of the diagram, either here or here, right? It can never, never, ever be here, okay, or here. And that gives why if we second order system will be asymptotically stable, okay. All kind of things we will discuss when we will discuss control, but the understanding is here. So for zeta not equals to, look here now, come back, zeta not equals to 1, we can consider case number 1 when zeta greater than 1, and we call system, if that is c by 2m greater than root over of k by m, and we called the system overdamped, and the situation is overdamping, okay. Solution will be overdamped, corresponding to overdamping situation, and zeta could be less than equals to 1, and we call system is underdamped. And third case, zeta equals to 1. So all these three solutions we'll try to crank out, okay. So again, for your convenience, I have written, rewriting the solution from equation 10, you have this, right? And case 1, zeta greater than 1, that is, or c by 2m greater than root over k by m. So here, so what is zeta square minus 1? This will be less than zeta, right? Always. So both the exponents are real and negative definite, and the solutions can be written as that motion will be aperiodic, because e to the power minus something, always amplitude will be decaying, decaying, decaying. There is nobody to make it oscillate, so there will be no oscillation. So wherever you see, wherever it starts from here, okay, it's amazing, right? So it will not be going back like that, okay, because of the damper. So wherever it is, it will try to, wherever it starts, it will try to just decay, right? X will be 0 after some time, after some t. What will be the t? That will depend on parameters m, c, k, etc., etc., right? So you see, you can draw this in MATLAB. It is a great, interesting thing to draw, that this is a solution now. This is a solution. Take any value a1, a2, and we can find them if the boundary conditions are given, okay, in many maths, you see, exercise problem which we will do in the class. This we will give concrete examples, and where A1, A2 you will figure out, and then in MATLAB, taking some value of zeta. Zeta is actually a fraction 0 to 1. Okay, so 0.1, 0.2, 0.3. So any damping factor you can take and you can plot, and you will see. But even you can see here, say this is alpha equals to zeta minus root over of zeta square minus 1 times omega, which is greater than 0. Okay, because this is less than zeta definitely, and beta also greater than 0. And you see beta is much bigger than alpha, isn't it? Because with this you are adding something which is a little bit small, and here you are subtracting. So this is the case, right? So what does it signify? It signifies that in overdamped situation, the solutions, depending on alpha and beta values, that is, which is dependent on zeta, the exponent which is attached to the beta value, it will decay faster than this, isn't it? This will decay faster. Just you can check it. It's very common sense. Okay. So this will be, there will be no damping. So motion will be non-oscillatory, no periodic motion. Okay. Now let us consider case 2, when zeta less than 1. That means c by 2m less than root over of k by m. And this situation is called underdamped situation. So what you are going to see, observe here, that if this is the situation, this will be negative. Inside the root, the quantity will be negative definite. So root over of, if I tell root over of minus 1 equals to I, then I can write the underdamped this quantity minus zeta plus I, which is root over of minus 1, and take minus common, 1 minus zeta square times omega t. Clear? Plus a2 e to the power minus zeta minus, same thing, you bring I, which is root over of minus 1. So in controls engineering, you know, quantity I, or sometimes it is denoted by J, which is imaginary quantity, they have physical significance. It's not that you will, you can only imagine that kind of thing. What is the physical significance? Significance is wherever there is root attached with the imaginary part, there will be oscillation. And why, you will see here. From Euler equation, you know, e to the power I theta equal to cos theta plus I sin theta. So imaginary part means oscillation. So here also, what is going to happen? Let us see. X equals to e to the power, just algebra. We are taking a is dashed sine 1 minus zeta square omega t plus a double dashed cosine 1 minus zeta square. So this is our equation, right? So putting 1 minus root over 1 minus zeta square times omega equal to omega d, that is damped circular frequency, and applying separation of variable principle. Now we will apply separation of variable principle. So here actually we have jumped some steps, and how it is coming, I will suggest, is very, very simple. Okay, you do this please. So e to the power I theta, so e to the power minus zeta omega t, okay, separates out, plus e to the power I root over of this, then there will be another e to the power minus I, right? So this, so now put e to the power I theta equal to cos theta plus I sin theta, and do some calculations. That will some copy will be filled up with beautiful symbols, but they're very simple. That's why I have avoided it. So just, and then pick them up and simplify, you will get this e to the power minus zeta omega t. This is constant, sine of this thing plus another constant cosine of this thing. Putting this for simplification, so this is called damped circular frequency. Damped circular frequency. Why? Because circular frequency is multiplied by a quantity which contains damping factor. Okay, and this is a fraction, right? 0.1, 0.2, 0.30, it varies from 0 to 1. So it will be always less than 1. So always the frequency will be damped, means it will decrease. Okay, so omega d is the damped circular frequency. And if you apply separation of variable principle, just like that, a prime equals to x sine phi, a double dash x cos phi, and tan phi will be this, phi equal to phase angle. We obtain the solution as x, small x equals to capital X e to the power minus zeta omega t times this. So you see, this is a quantity which is having dampening effect on the oscillation. So whatever quantity this might be, e to the power minus something. So wherever it starts, right, the amplitude of oscillation will be decaying because of this quantity. Okay, and with that decaying amplitude, it will oscillate because sine term is there for zeta less than 1. That is when the system is underdamped. So what is the take home? If the system is underdamped, there will be oscillation. Okay, damped oscillation. Why? Because oscillation will not be like this. Okay, but it will be like this. First amplitude is this, then this, then this, then this, and then it will die down. Huh? So this is just like our coronavirus wave. So it will start from somewhere with initial condition, right? And now I am not drawing this one. So it will have plateau, then again it will come off, second wave, then again it will come off, and ultimately it will die down, not die down, it will be there with small oscillations, and we'll have to live with that. Okay, so we'll have to open up our institute, open up everything, and we'll have to live with the virus. So even that you can just model, see from here. So you see this beautiful graph I have drawn. Okay, how maybe in the next class we'll start from here. This is very important, and maybe we'll discuss right from here that that under damped situation will make sure that the system oscillates. Okay. So with this, I would like to conclude for today, and tomorrow we'll start from here, and we'll draw your attention to critical damped situation as well. Till then, stay safe. Have a nice day. Bye bye.